Welcome to today's video. After the introduction of the Riemann integral, it is now a good time to have a look at some elementary properties of that integral. Pretty much all of those should be familiar from real valued integration, so the following theorem should be no surprise. So that's basically just a summary of these important properties that you already know. So the setting here is as usual. We'll take a box. So let B subset of R to the n be a box. We'll take two parameters, alpha and beta, real numbers. And we'll take two functions, f and g, defined on that box, that are Riemann integrable. Then the following properties hold. First, the Riemann integral is linear, so that's linearity. That means the function alpha f plus beta g is Riemann integrable with the integral of that function alpha f plus beta g of x dx over the box B is the same as alpha times the integral of f of x dx over the box B plus beta times the integral of g of x dx over the box B. So that's linearity. The second property is known as monotonicity. And it says if the function f is less or equal to the function g over b, so for all x in b, then this relation is also true for the integrals. So then the integral of f of x dx over b is less or equal to the integral of g of x dx over b. The third property is a relation about the absolute value of a function that says if a function f is Riemann integrable, then so is its absolute value. So the function x maps to absolute value of f of x is Riemann integrable with the following relation: the absolute value of the integral of f of x dx over b is less or equal to the integral over the absolute value of f of x dx over b. Again, something that is familiar from one-dimensional theory. And finally, point 4. Something that we'll use often is every continuous function is Riemann integrable. Because pretty much for every continuous function, the infimum and the supremum over those boxes exist, and they're actually the maximum and the minimum. And we can also show that this process of taking lower and upper Riemann sums converges to the same value for continuous functions. We won't go into detail here, but it's not hard to show that. So every continuous function h b to r is Riemann integrable. And of course, there is a number of functions that are not continuous, but still Riemann integrable. So the other implication is not usually true. Every continuous function can be integrated, but if a function can be integrated, that does not necessarily imply it's continuous. There are lots of functions that can be integrated and that are not continuous. Okay, so this concludes this simple short list of elementary properties of the Riemann integral for today. Thank you for your attention.